The next speaker is Michael Oppenheimer, and he will talk about Earth's ice sheets and sea level rise, insufficient data, inadequate models, and an urgent need to know.
It really is a pleasure and an honor to be invited to speak here. Alex was fundamental to getting me started in my career. I came here as a postdoc. And it was an incredibly exciting time because Bill Klemperer had just done his groundbreaking work on astrochemistry. Every week there would be 2 or 3 new interstellar molecules discovered. It gave people a lot to do in trying to explain why those molecules were there. I have no idea whether those explanations turned out to be true or not, but in a way, some of them were, some of them weren't. It kept us very busy. And it's great to see some old friends here who I did work with. I see Charlie there, who actually gave me the opportunity to go do some observations. I once actually got near a telescope with Charlie and Barry Schneider, who I actually know going back to graduate school when I was an experimental physical chemist, and I got out of that quickly because I thought if I stayed any longer I would kill myself. I was a danger in the laboratory. And I came to the observatory, and the observatory was very kind to me. Alex was very kind in being flexible, letting me try new things and go wherever I wanted to go intellectually. And actually, when I think about what you were doing and the scope of what you've done, not just in atomic physics, but really what's impressive is that you were fearless in the applications. Go anywhere, do anything, any part of the universe, big, small, let's take a look at it. That, I think, ultimately is what I learned here. And that, I think, is the big lesson that set me off to go where I went later in my career, which has very little in a direct sense to do with anything that's done at the observatory now, as far as I understand it. By the way, the last time I was invited back here to give a talk was 15 years ago at the Symposium associated with your 65th birthday, I think. It was a Festschrift or something like that, and I'm looking forward to your 95th. I hope we can come back again and do the same thing. I stretched my mind to try to make a connection between what I do now and what I did then and some of the specifics that were done here. Right now, I'm working on global warming, and I have a specific interest in ice sheets. The big problem with ice sheets is that we don't know what the hell they're going to do. They're doing a lot of things now that are unexplained and perhaps unexplainable in any reasonable time frame. So what I try to do is try to figure out what is the connection between the way we approach problems when I was working on planetary atmospheres, comets, the interstellar medium, and what I do now. And there are some things in common, and I actually do believe that the experiences I had that Alex trained me for have stood me in good stead later in trying to think about these other earthbound problems. Like the interstellar medium, ice sheets are remote in a very real sense. There are very few observations. The models of them are very poorly constrained by observations, and they don't do very well at predicting what the ice sheets are doing right now, unfortunately. You can't haul an ice sheet into a laboratory and play games with it, but much as there were at that time for observing the planetary atmospheres and interstellar medium, there are a lot of very elegant tools for trying to understand what ice sheets are going to do. Probably the most elegant one is an experiment called GRACE, where you have 2 satellites which are teamed up, which fly in tandem. And the small adjustments that are made, the small differences in their orbits and the changes in those differences over time are used to infer changes in the mass balances of the ice sheets. That is, they are big enough and the changes in them are substantial enough to affect the relative trajectories of 2 satellites. Everybody in my business loves that experiment. There are some issues with interpretation, but that'll settle down over the next 10 or 15 years. Key to all this is using small-scale properties which you know very precisely to get a window into the behavior of very large-scale systems that you know virtually nothing about. And I'll never forget the time I walked into Alex's office, and I think John Black was there. This probably meant nothing to you, but I've never forgotten it. And Alex was explaining how we were going to take, I think it was 21 centimeter observations of hydrogen atoms and trying to infer the radiation temperature from the relatively precise observations, and use that in turn to say something intelligent about the thermodynamics of these big interstellar clouds. I never got over that you could use a microscopic observation to work backwards and say something about something that big. And really with ice sheets, there's a similar thing that goes on. I may be stretching the analogy, but the immense amount of information that's come from ice cores that are drilled into the center of Antarctica, Greenland, and tropical glaciers, are then pulled up and looked at and analyzed in great, very careful detail in a laboratory. The analyses are very precise. And from those, you can determine, if you have enough ice cores, the large-scale behavior, both the current behavior and the long-term history of these massive ice sheets. And to flip that around, just like the microscopic properties of atoms and molecules drove the thermodynamic behavior of these gases that we talk about, there are very small-scale properties that have to be understood with high precision to be able to predict the behavior of ice sheets. For instance, under the big ice sheets is a lot of water, and it occupies small spaces. And little rocks and bumps that are basically a very small scale compared to the whole ice sheet really determine how fast the ice is going to flow, what the mass balance is, and ultimately how global warming will affect the future of the ice sheets. And making that link between the small scale and the large scale is something I would not have thought of had I not worked here first. Another similarity is the boundaries of these monstrous things, both the ice sheets and interstellar clouds, I don't know if they still are, I don't know a damn thing about interstellar clouds these days. So please, excuse any ignorance I reveal. But at that time, the boundaries were totally elusive. A big problem at the time is, why do these large-scale features exist? What pens them in? Why do you get structure? I'm sure that problem hasn't been completely solved. Well, an analogous problem exists with ice sheets. If you want to know the truth, we don't know why so-called marine-based ice sheets like the western part of Antarctica exist. We don't know why they're stable. We can't predict their coming into being. We can't predict that they're disappearing. They do not have stable boundaries as far as we know. So we do not understand why they exist at all. Such is the depth of our ignorance. And finally, and most importantly, I learned to speak in two tongues. I learned to speak with very high precision about the atomic scale while talking at, orders of magnitude uncertainty about the large-scale properties. And it's the same thing when you talk about Earth systems. Again, the small-scale things that you can talk about with high precision drive large-scale processes for geographically large phenomena that, you really have to throw up your hands sometimes as far as knowing what's going to happen. Now, what I'm going to talk about in the 20 minutes or so that I have, so it'll be seriously abbreviated and simplified, is the question of ice sheets and sea level rise. Why are ice sheets a key factor in projecting future sea level rise? What is an ice sheet anyway? I bet if you think about it, you're really not sure. And what will the behavior be as the Earth warms? One thing we do know with high precision is what sea level has been doing over the last 100 years or so. For most of the last 100 years, there was a network of flotation devices called tide gauges, which it turns out, in retrospect, were measuring sea level with great accuracy. There were two networks, essentially, over time, the red one and the blue one. Then recently, we got satellite data, which is just this last 15 years or so, and it turns out the two things are smack on top of each other. So that we now believe we have a very, very accurate picture, geographically and temporally, of the changes in Earth's sea level, and we'll be able to have that picture going forward. Sea level rose about, and I'm going to be switching units back and forth here. Sometimes I'm going to talk meters and sometimes millimeters, just because it doesn't make sense to talk thousands of millimeters. But in any event, 0.2 meters has been the approximate sea level rise, about 20 centimeters over this century. And if you don't think that's a lot, on your typical East Coast beach, 1 meter of sea level rise takes away 100 meters horizontally. in terms of erosion and submergence. So it's a big deal already. This is one reason the coast is a slippery thing, and this is one reason houses go into the drink perpetually. In fact, while storms are believed to reconfigure the coast, like northeasters or hurricanes, and move it in and out, over time that would average to zero change, it is now believed, except for the slight long-term drift upward in sea level, which effectively takes away the coastline. So the recent rise has been an average over the era of the satellite data of about 3 millimeters per year, which is about 50% faster if you did a century average for this number. So there's been an acceleration. That acceleration is believed to be tied to the warming trend. And in order to explain that acceleration, you have to invoke changes in Earth's ice sheets, primarily Greenland and Antarctica. Now, just without getting into detail, we can project, the global climate models, which are in a lot better shape than the ice sheet models, project a warming of about 1 to 6 degrees Celsius over the 21st century. It's a big difference. 1 degree is modest. We notice some change. Most countries would successfully adapt. A 6-degree warming in a century is believed by most of my colleagues to be catastrophic. And we don't know which end we'll get or where in between. There are 2 reasons for this big uncertainty. We don't really know with greater than about a 50% accuracy what the sensitivity of the climate is to any increment of greenhouse gas increase in the atmosphere. And we certainly don't know what emissions are going to do. 10 years ago, no one was I would say no one, most people were not predicting such a rapid increase in developing country emissions from, say, India and China. On the other hand, to project forward and say these kinds of massive rates of growth, 8, 9, 10% are going to continue is ridiculous. We simply don't know. So a range of scenarios is considered. And the question is, for that temperature range that we believe is plausible, what is sea level going to do? There are 3 components to sea level rise. There are actually many more, but temporarily the other ones are written off as not important. I'm not sure that that's true, but we'll see. Glaciers. If you think about the ability, and here I mean mountain glaciers and small ice caps like Iceland, they only contain about ½ a meter of sea level rise worth of ice. Even if you melt them all away, you only increase sea level by about ½ a meter. And the rate at which it can happen is not all that fast, so you would expect something like, C is century here, so about 1/10 of a meter per century is roughly the rate. Maybe it'll double in the future as the Earth warms. The current rate is 0.08 meters per century. Thermal expansion. Most fluids expand when you heat them. It takes a while for the heat to percolate down to the lowest levels of the ocean, so the expansion happens in a lagged fashion compared to the warming. Ultimately, this itself could create a few 2 or 3 meters of sea level rise, but over many hundreds or maybe several thousand years. It's also a gradual process because of the long time for heat to diffuse to the bottom of the ocean. And so the rates are of the order of 0.1 to 0.3 meters per century. So adding these 2 pieces together, and by the way, this is the current rate, right about in the middle of that, you would expect over the coming century a few tenths of a meter, 3, 4, maybe at the outside 6/10 of a meter, according to the Intergovernmental Panel on Climate Change, of sea level rise from these 2 sources. But look at this one. This is what the ice sheets could contribute, 64 meters. That's the total volume of sea level equivalent in Greenland and Antarctica. And we don't know what the rates are. We don't know how fast it can disappear into the ocean as Earth warms. There is what's called paleoclimatic evidence from old climates that we have fossil data for, that these ice sheets could dump ice into the oceans at the rate of equivalent of 1 to 2 meters per century. That's a very, very big deal. You're talking about an order of magnitude greater than these 2 other sources could contribute. Right now, the ice sheets are disgorging at a net of about 0.4 meters per century, which is quite a bit larger. Actually, I'm sorry, there's a decimal point missing. This is 0.04. So it gets close to what the glaciers are doing. But what's interesting about this is the expectation was they wouldn't be doing it at all. The reason for that is it was expected that precipitation would increase in a warming atmosphere because the atmosphere can hold more moisture. That would be reflected in increased snowfall over Antarctica and the center of Greenland. That would cancel any loss due to warming at the edges. That has not happened. Precipitation has not increased in the middle of Antarctica in particular, so the loss of ice has come to dominate. The ice sheets are very slowly frittering away. Key question is, Can it go quicker? If so, how much quicker? There are really three sections of ice to worry about. Greenland contains about 7 meters equivalent to sea level rise. The western part of Antarctica is an archipelago. It's an archipelago with a big chunk of ice in the middle that's sitting on the bottom of the ocean. That contains an equivalent of about 5 meters of sea level rise. The big one here, East Antarctica, contains 57 meters, according to the latest reckoning. Most of this ice sheet and almost all of this ice sheet are above sea level. They are not believed, by and large, to be vulnerable to rapid loss. This one, because it's bedded below sea level, is believed to be potentially subject to very rapid discharge, that is, several meters in several centuries, a very large rate of sea level rise. What's the hazard? Modern Florida, this is depends, well, let me go over them individually. Modern Florida today, Florida without the Greenland ice sheet, Florida without the Greenland and West Antarctic ice sheets, that's about 12 meters of sea level rise. This is, if the East Antarctic ice sheet were to go, water world, it's not believed to be much chance it would happen. But of that 57 meters of sea level rise equivalent in East Antarctica, about 6 of it is vulnerable because it's tied to ice streams, which I'll explain later, rivers of ice which are moving fast and which drain areas which are below sea level. So while this can't happen, something like this and even a little more could happen. A little more, some more of this stuff. This is the red area is the area of the middle Atlantic region, which is below 6 meters sea level rise. Again, if either the West Antarctic ice sheet or the Greenland ice sheet were to deteriorate, you'd get a pattern like that. And this is the area of the Gulf Coast that we worry about because of hurricanes. Well, the dark green area is the area that would be underwater if both the West Antarctic and Greenland ice sheets, plus counting in the thermal expansion part, added together, you get about 15 meters of sea level rise. That would be underwater. That's the plausible outside range of what sea level rise could do over the next few centuries. It gets worse in developing countries where there are large river deltas and not much to be done in terms of protecting them. So for instance, Netherlands has a very elaborate system of works to protect it from the ocean, which they're planning on accommodating to this kind of sea level rise by raising the dikes. Those kinds of resources are at this time at least not available, and the gaping opening, for instance, in this case of Bangladesh, into the Bay of Bengal is just too big, I think, to build any kind of sea defense. So for instance, if sea level only goes up 1 meter, this whole area goes underwater. 3 meters takes you back to the capital, Dhaka, and about half the country is underwater. Just in this area, about 10 million people live right now. Where are they going to go? So what is an ice sheet? An ice sheet forms when snow falls in the center of one of these very cold continents. And as it accumulates in a pile of snow, it just doesn't sit there. Gravity will squeeze it, squish, force it towards the edges of the continent. When it gets to the edges, it's near the ocean. The ocean's warm. You form icebergs, or you start melting, because you think about the configuration here. This part of the ice sheet is at lower altitude than this part, so it's warmer anyway, plus it's marine influenced, so the ice sheet starts to melt away. It makes a big difference. This ice sheet is like the West Antarctic ice sheet, with the bed being way below sea level. Here's sea level. And again, we don't know how to hold the boundaries on this ice sheet. There's something called an ice shelf here, which is floating ice, which we think is playing some role, and I'll talk about that later, but we're not 100% sure. It is this relationship between a sea level up here and a bed of an ice sheet down here, which we think leads to instability. This is, if like Greenland, the level of the sea is right there where the red line is, it's much harder to get an unstable ice sheet. So for my money, I'm more worried about Antarctica than Greenland. So the other thing you should know about ice sheets is that they're wet at the base. Because there's several kilometers of ice here, they're effectively insulated from the atmosphere, and the geothermal energy working its way up from deep in the earth accumulates at the base of the ice sheet and starts melting it. So oddly, ice sheets are wet at the bottom at many places. 5 minutes? Are you intimidating me for some particular reason?
Yeah, you've got 10 minutes.
Okay. Oh, good. That's nice.
Including questions.
The other thing about ice sheets is the West Antarctic ice sheet sits in a marine basin. That is, it wasn't always there. The ocean used to be in there. When the ocean was there was a lot of sediment from biological activity and also clay-like sediment that was brought in by the glaciers sweeping in and out of there that sits at the bottom. That stuff is like a slippery layer of lubrication. So the concern is that that wet, slippery base would eventually let the ice sheet slip into the ocean if the edge is warm enough so it gets unstuck from the rocky coast over here. So it's the ice shelves seem to play the role of jamming the ice sheet against a rocky coast, and if those ice shelves, which are floating in warm ocean water, start to melt away as the ocean water gets warmer, then it's potentially the case that the ice sheets kind of rapidly, in century timescales, slip into the ocean. Ice sheets melt also, and the direct melting is probably the main reason Greenland is losing ice right now. The red area is the area which this ice sheet is melting, and the area is increased as the world is warmed. This is the data just for the last 10 years. When the ice sheets also flow, as I said, they don't just sit there, and their flow is very highly organized in features called ice streams. The ice streams look like rivers of ice. This is not a rocky area. This is static ice frozen to the bed, more static ice. This is moving, a few hundredths of a kilometer per year. This is moving a few hundredths of a kilometer per year. This is moving fast for a glacier, about a kilometer per year. If you calculate it, think about how much ice can be mobilized that way. It's a lot. The influence of these ice streams reaches way back into the center of the ice sheets, and it is believed can literally pull the ice out into the ocean area here. This merely shows that both ice sheets are now losing ice. We can model the melt aspect of ice sheets very well. We have a good idea of why they melt, how they melt, and what the response to warming will be. We can model the movement of the slow ice, that's this stuff, the relatively static ice, but we don't know how to model this. And because we don't know how to model those ice streams, we basically have zero skill at modeling ice streams. And because they are the major determinant of the ice loss of these ice sheets, we have no way to predict the future, particularly for Antarctica. Again, the theory is, the prominent theory now is that if one of these ice shelves is to melt away as the ocean water, the blue stuff warms, that'll unhinge the ice shelf and the ice sheet from bedrock and allow this slippery lay to guide these ice streams into the ocean. There are 4 areas of Antarctica, 1 in East Antarctica, as I mentioned before, and 3 in West Antarctica, where we think this process could occur. And we recently got a natural experiment when an ice shelf along the Antarctic Peninsula, the part that points towards South America, collapsed rather suddenly. It was thought that as it started to melt away due to warming, this is a very warm part of Antarctica, it would take many centuries for that ice shelf to disintegrate as it warmed. But in fact, it shattered very quickly. Here's the ice shelf on 31 January 2002. The dark areas are melt ponds in the surface. Turned out that meltwater percolated down through cracks in the floating ice, and 5 weeks later it was like that, completely disintegrated. A huge feature. This is hundreds of meters thick. And boom, gone. So, and the other thing we found out from this experiment is that the glaciers behind this ice shelf, the wide ones which are not impeded by rock, started accelerating into the ocean. So that loss of an ice shelf did make a measurable contribution to sea level rise. Fortunately, this part of Antarctica is skinny and doesn't contain much ice, and even if we lost the whole thing, it wouldn't be a big deal. The trouble is there are much larger ice shelves to the south. Wait a minute. Let me show those here. Here, the Ross ice shelf, the Filch-Durrani ice shelf, and the smaller ice shelves in the Amundsen Sea area, which together appear to pen in about 5 meters of sea level equivalent. This area has started to go already, and it may be that we are brought into 1.5 meters sea level rise no matter what we do. We simply don't know. In the interest of time, I'm going to sum up quickly. The same processes seem to be underway in Greenland in a few places, I should mention. The only way to get a handle on this situation, given that we don't have a good model for projection, is to look at ancient climates. This is the famous picture of ice core data. The blue are carbon dioxide levels in ice cores going back from today back through 4 glacial cycles 400,000 years ago. The data now go back out here to 800,000 years. The T is the inferred temperature of the atmosphere, something you can do with isotope data. I won't go into it now. The last time Earth was as warm as today was about 130,000 years ago. Temperature was actually a little warmer than today up here. The poles, because of the inclination of the Earth's orbit to the Earth's axis to the sun, was 3 to 5 degrees Celsius warmer than today. A temperature we shall reach in this century if we don't restrict the emissions of the greenhouse gases. And in fact, a temperature we could be committed to reaching within a few decades of unconstrained emissions. At that time, it turns out, Greenland was probably a few meters of sea level rise equivalent smaller. We don't know what Antarctica was doing, but we do know that rates of sea level rise, these are inference as far as what sea level was deduced from coral stands. There were some episodes of very rapid sea level rise, which suggest that either the Greenland or the Western Arctic ice sheet or both were discharging ice at the rate of a sea level rise equivalent of about 1 meter per century, maybe 2 meters. So the bottom line on it is this. Best of our knowledge, based on the paleoclimate data, is that large sections of one or both of these ice sheets are vulnerable for only a 1 to 4 degrees Celsius warming above current temperature. At least a slow, if that happens slowly, if we don't do anything about emissions and that happens slowly, that is millennial scale, a couple of millennia to lose 6 to 12 meters, it would be manageable. We'd lose a lot. We'd lose huge amounts of coastal area, but we wouldn't be running for our lives, literally. But if it happens on century scales, which is what the paleoclimatic data suggest happened in the past, then you're talking about rates of 1, maybe 2 meters per century, and that would certainly be catastrophic in many coastal areas. So while we're working on these models, one of the things I'm doing now is trying to get together, get the Geophysical Fluid Dynamics Laboratory at Princeton to put together a state-of-the-art model. That'll take, 15 or 20 years. It'll be way past the next Dalgarno Symposium by the time a model is complete and validated. We really need to get serious about emissions reductions now, or else there just ain't going to be any coastline left, at least not where it is. Thank you. Do you have any time for questions?
Michael,
is that Ray Flannery?
This is reincarnated from your past. The ghost.
I thought I'd gotten away from you.
Now we're here. Now, Michael, your little cartoon on Florida, in the paleo times was actually extremely realistic because Florida did not exist there. In fact, most of southern Georgia did not exist. The sea was right up against the Smoky Mountains, North Georgia.
A long time ago,
in fact,
though.
anytime I go up there, I can actually pick up seashells in the sediments of the mountains. So maybe we're in some cyclic situation.
There is certainly a natural cycle. We are certainly accelerating it at this point.
So there. Thank you, Michael.
Thank you, Ray.
Michael, hello. I'm Gordon Drake.
Hey, how are you?
I was just wondering, is there really evidence that your graph showing the increase in sea level seem to be pretty well linear? If there's an anthropogenic component, wouldn't you expect to see an upward curve?
There is an upward curve. If you go back a millennium, the rate of sea level change was no greater than about an order of magnitude less than it is starting at about 1800 or 1850. You can't, you don't have good decadal numbers going back before about 1900. Then it starts to accelerate sometime around the end of the 19th century.
But isn't that
And
still a
then-
bit too early for it to be, I mean, most,
No.
since 1950 is when
No,
would
you can model it. And the amount of warming that was built in already from the CO2 increase that really starts in the data sometime around 1800 or 1750 is sufficient to explain the gradual rate of sea level rise. The rate of sea level rise in the past is pretty well explained until the last 10 years. Something changed, and what's believed to have changed is the engagement of the ice sheets.
Very interesting.